Welcome to this deep dive into the symmetric tree problem. We are given the root of a binary tree and must determine if it is a mirror of itself. What does it mean for a tree to be symmetric around its center? Let's visualize this with example 1. Imagine a vertical dashed line passing directly through the root node. For the tree to be symmetric, the entire left subtree must be an exact spatial reflection of the entire right subtree across this central axis. Let's analyze the first level below the root to see this reflection in practice. The left child of the root has a value of 2. The corresponding reflected position on the right side is the root's right child, which also has a value of 2. Because these values are equal, the symmetry holds at this specific level. However, a single level match is insufficient. We must rigorously verify the structural and value symmetry for every subsequent level down to the leaves. Moving down to the next level, the comparison becomes a cross-check. The left child's left node, which is 3, resides on the outer left edge. Its mirror reflection is the right child's right node, on the outer right edge, which is also 3. Similarly, the left child's inner right node, 4, must be compared with the right child's inner left node, 4. Notice how outer nodes compare with outer nodes, and inner nodes compare with inner nodes. Contrast this with example 2, which demonstrates a failure of symmetry. The root's children both have a value of 2, so level 1 passes. But look at the next level. The left child's left node is null. It does not exist. Its expected mirror position is the right child's right node, which contains the value 3. A non-existent null node cannot reflect a node with a value of 3. Because structural existence fails to match here, the entire tree is asymmetric. To translate this visual cross-checking logic into a rigorous algorithm, we need a mechanism to compare two distinct subtrees simultaneously. We will define a helper function named is_mirror. This function will accept two node pointers as arguments, which we will call t1 and t2. To initiate the process, t1 will point to the root's left child, and t2 will point to the root's right child, allowing us to traverse down both sides concurrently. For the subtrees rooted at t1 and t2 to be perfect mirrors, 3 specific conditions must be satisfied simultaneously. We will combine these using a logical AND operation. The first and most fundamental condition is value equality. The data stored in node t1 must be identical to the data stored in node t2. We write this algebraic step as t1.val equals t2.val. If these values differ at any point, the mirroring property is immediately broken. The second condition dictates that the outer edges must mirror each other. We enforce this by recursively calling our helper function to compare t1's left subtree with t2's right subtree, is_mirror of t1.left and t2.right. The third condition handles the inner branches similarly. We must recursively compare t1's right subtree with t2's left subtree, is_mirror of t1.right and t2.left. Only when all 3 of these Boolean conditions evaluate to true can we say the subtrees are mirrors. Before we write the recursive logic, we must address a critical pitfall: missing base cases. As our pointers t1 and t2 traverse downward, they will eventually reach the bottom of the tree and attempt to access the children of leaf nodes, which are null. If we do not explicitly define how our function should handle these null pointers, our program will crash with a null reference error or enter an infinite loop. Let's rigorously derive the first base case. What is the mathematical outcome if both pointer t1 and pointer t2 become null at the exact same time? This scenario means we have traversed paths on both sides of the tree and found no mismatches, reaching empty space simultaneously. Two completely empty subtrees possess identical structure and no conflicting values, so they are, by definition, mirrors of each other. Therefore, we must return true. Now we derive the second base case. What happens if only one of the pointers is null? For example, T1 points to a valid node, but T2 has reached a null state. This represents a structural mismatch, exactly like the one we analyzed in example 2. A physical node can never be the mirror reflection of an empty space. In this specific scenario, symmetry is broken, and we must return false. Let's assemble our derivations into the final Python code. We start by defining the main class method, isSymmetric, which receives the main root node. Our very first algebraic step is to handle the global edge case. If the provided root is null, we are dealing with an entirely empty tree. Since an empty tree is perfectly symmetric around its non-existent center, we evaluate this condition and immediately return true. Next, nested within our main function, we define the recursive helper function is_mirror, taking parameters t1 and t2. We immediately implement the two base cases we derived to protect our recursion. First, if not t1 and not t2, we return true. Second, if not t1 or not t2, we return false. Note that because the first statement catches the double null scenario, the second statement strictly catches the asymmetric single null scenario. If execution passes both base cases, we are mathematically guaranteed that both T1 and T2 are valid nodes. Now we translate our three pillars of symmetry into a single, rigorous Boolean expression. We return the evaluated result of T1.val equals T2.val, logical, and the recursive call is_mirror of T1.left and T2.right, logical, and the recursive call is_mirror of T1.right and T2.left. This continuous chain elegantly enforces all required spatial reflections. Our helper function is now completely defined, but it remains dormant. To trigger the symmetry verification for the entire tree, we must initiate the first call from within the main isSymmetric function scope. We execute is_mirror, explicitly passing root.left as the initial t1 argument, and root.right as the initial t2 argument. We then return the final Boolean result produced by this initial, top-level recursive chain. Let's rigorously verify our algorithm by tracing example 1. The main function receives node 1 and calls is_mirror with the left child, node 2, and the right child, node 2. Inside is_mirror, the base cases are bypassed. The value check evaluates to true because 2 equals 2. The function then evaluates the first and condition, pushing a new frame to the call stack to compare the outer nodes, 3 and 3. That recursive call for the outer nodes will eventually hit the double null base cases for their children and return true. Concurrently, the algorithm evaluates the second and condition, initiating a call to compare the inner nodes, 4 and 4. This also validates and returns true. Finally, the expression resolves to true and true and true, yielding a final result of true, confirming the tree is symmetric. Our derivation is complete and verified. Let's finalize with complexity analysis. In the worst-case scenario, where the tree is entirely symmetric, our algorithm must visit every single node exactly once to verify the structure. Therefore, the time complexity is big O of n, where n is the total number of nodes. The space complexity relies on the recursive call stack, which reaches a maximum depth equal to the tree's height, resulting in a space complexity of big O of h.